Yeah, that's me again, and I'm going to tell you today about stable and unstable nuclei and then going on some decays. Alright? So, first of all, we need to know about the strong nuclear force. So, if you have a stable isotope, the nucleus does not disintegrate, okay? So, the nucleus does not fall apart. Now, in case you do not remember what an isotope is when you have an atom that has the same number of protons, but a different mass number, meaning that the number of neutrons is different, okay? Now, the force that holds the whole thing together is the strong nuclear force. And when I say the whole thing together, I mean the nucleus. Now, here, as you can see, the definition of the strong nuclear force is going to be the attractive force between the nucleons, so protons and neutrons, that holds the nucleons, protons and neutrons, in the nucleus. So basically, it makes that the nucleus does not disintegrate. Everything is attracted to each other, okay, or to the other particles. And then this force, if you have a stable isotope, is overcoming the electrostatic force of repulsion between the protons and the neutrons in the nucleus. Okay? So that's about the forces. Now, how does this work? So if you have an isotope, it can be stable or unstable. If it's stable, just as we mentioned, the strong nuclear force is going to overcome the electrostatic force of repulsion between the protons and the neutrons in the nucleus. And then the nucleus does not disintegrate. If it's unstable, then the opposite happens. So the strong nuclear force cannot overcome the electrostatic force that is trying to get them to go further away and apart from each other, and therefore the nucleus disintegrates, okay? Now, how does this work and how we can predict if something is stable or unstable? Let's look at this picture in here. That's going to be my atom, okay, that's the nucleus, and here I have some different colored arrows. So I have arrows going outwards actually, which are here orange, and that's about the electrostatic force. So this electrostatic force is the one that is trying to get the neutrons and the protons apart, okay, to so that they repel each other. Now, the range of this force is an infinite range, but it decreases with distance. So if you look here in this diagram, that's the electrostatic force is quite big in the beginning, and then as the distance increases, the force decreases, okay? On the other hand, trying to fight against this force is the strong nuclear force, which is here in purple, okay? We have the range showing, and then we have the arrow showing that it goes inwards. So it's kind of an attractive force between the protons and the neutrons, all right? Now, the range of the strong nuclear force is about 3 to 4 femtometers, which is Fn, okay? In case you don't know, a femtometer is equal to 10 to the power of minus 15 meters. And again, here we have in the diagram, in the graph here, the strong nuclear force. It does have a peak, and then it has this line, and I will explain this line in a second, okay? Now, if you think about the nucleus of normal atoms, so we are just talking about a normal atom with a small nucleus, 3 to 4 femtometers is about the same as the diameter of that nucleus, okay? So it means that the range of the strong nuclear force is big enough to be able to get that a small nucleus does not disintegrate. But then when we get a nucleus with more neutrons and more protons, then they are going to be above this number, and therefore is more likely that they become unstable and therefore disintegrate. Now, regarding the range of the strong nuclear force, as you can see, is attractive, but then we have this line in here, right? Now, this line is because at 0.5 femtometers, and again a femtometer is 10 to the power of minus 15, the strong nuclear force becomes repulsive, okay, and prevents the neutrons and the protons being pushed against each other. So that's why we have that line in there, okay? Now, when you have a nucleus, an unstable isotope and the nucleus disintegrating, you can have alpha, beta, or gamma emission, or more than one happening at once, okay? So, in radiation, we have alpha, beta, and gamma, and as we know, the alpha radiation is the same as the helium nuclei, okay? So, you put the symbol alpha, the Greek letter alpha, and then the mass number is 4, and the atomic number is 2. You need to know this by heart. So is the most ionizing of all, is the least penetrating, is stopped by paper or a few centimeters of air. Then we have the beta. Beta is the same as the fast moving electron, okay? And again, that's the symbol, the beta, the Greek letter. And then we have mass number of 0, because we are saying that the electron has no mass in here, basically. And then the atomic number -1. So it's an electron, is opposite to the proton, so we are going to put a -1 in there, okay? And beta is stopped by thin aluminium. Finally, we have gamma. Gamma is an electromagnetic wave. And again, we represent it with the Greek letter and then 0 for mass number and 0 for the atomic number. From all the types of radiation, is the least penetrating, the least ionizing, as you could see in here. So the one that carries the least energy is the most penetrating though, okay? And is stopped by thick leads. Now, when we have the decays, I'm going to tell you about alpha, beta, and then a little bit about gamma, and ignore the animations happening in here. So, alpha decay, I have the nucleus in the beginning, and then it disintegrates and creates a new nucleus, smaller, plus an alpha particle. So, how do we figure out how the equations work? So, my mother nucleus is here, the X, atomic number of Z, and mass number of A. And then when it decays, if it's going to give an alpha particle, then I need to have an alpha particle with a mass number of 4 and the atomic number of 2. Now, how do I figure out the numbers here for the daughter or the product nucleus? What I need to think about is like this as a mathematical equation, where instead of an arrow I have an equal sign, and everything that happens before the decay must equal, in terms of numbers, everything that is happening after the decay. So, if my atomic number in the beginning is, mass number in the beginning is A, then I need to have A minus 4 for the new mass number of the nucleus Y, because A minus 4 plus 4 gives me A. If my atomic number in the beginning is Z, then the new nucleus Y must have Z minus 2, because Z minus 2 plus 2 gives me Z, okay? The same applies for beta. So, if I start with the mass number of A and atomic number of Z, then I will get a new nucleus. I'll go to this part in a second. A new nucleus Y plus the beta particle, mass number of 0 and the atomic number of -1. So I must have A as the new mass number, because A plus 0 gives me 8. And then the atomic number for the Y must be zeta plus 1, because zeta plus 1 minus 1 gives me zeta again, or Z again. I don't know why I'm saying zeta. And then I have this thing in here, okay? So this is a mu, and that's going to be, the mu alone is the symbol for a neutrino. But because it has a hat in here, I call it a hat, this line, it means that it's an antiparticle. So in this case, it's an antineutrino. So every time I have a beta decay, I have an antineutrino that is given as well, okay? So let's see here, talking weird, the steps for the beta decay. So, number 1, the nucleus has too many neutrons, and the neutron in the nucleus is going to change into a proton. Later on, you're going to see how this happens, okay? Then, when this happens, a beta particle is created and is emitted straight away. And then I get as well an antiparticle with no charge, which is called the antineutrino, and that's the symbol again, that is also emitted. Finally, about gamma decay, there's not much more to say, but I can tell you that it happens following an alpha or beta emission when the nucleus has way too much energy, okay? So, that's all for what I have today for now for the stable and unstable nucleus, and we are going to talk later on more about these decays, even do some Feynman diagrams and talk about all the things that really make here the neutron and the nucleus changing into a proton, okay? But for now, that's it, so stay tuned to see how cool physics is. Bye!